So then it's my pleasure to kick off the spring 2021 semester of PAW with a very special guest. So today we have Sasha Volberg, who's going to talk to us about biparameter Carleson embedding. Sasha.
Thank you very much. So it's my latest love. It's a very exciting topic, and it's exciting because it's a multi-parameter. So multi-parameter singular integrals, it's a very good subject, which you basically can study in a very short time, because there are maybe only 10 or 15 papers, or maybe 20 in the whole subject. It started in the 70s. Extremely good people were writing the results. So Jean Linjournet, Jill Pfeiffer, Carleson, Alice Chang. But multi-parameter, well, Tao, Thiele, Muscalo, but multi-parameter theory has very special flavor. It's quite combinatorial. So I will explain now a couple of things which we did. There were several papers with different co-authors, and here I wrote my main co-authors of those papers. So first I will explain just what is Carleson embedding in the simplest case. No multi-parameter, just one parameter. So one parameter, Carleson dyadic embedding. Embedding is the following problem. It was solved by Carleson. So you have a unit interval. You can think that it's a base of the unit square. Then you have dyadic subintervals always. Let's call them I. By the way, all functions, all measures, everything will be non-negative. So on the first glance, there are no single integrals, but actually it's an important building blocks of many single integrals. So I's denote, Ij denote dyadic intervals. 0, 1 is the first one, and f is non-negative function on 0, 1. And this symbol means that we just integrate and divide by the length with respect to Lebesgue measure. So everything is positive. So the question was to give a sort of nice, necessary, and sufficient condition for this to happen. So we want that for all functions, we would have this inequality. So why it's called Carleson embedding? Because what's going on, you consider the following geometric picture. So I is like a root, I equals 0, 1 is like our root. And to it, this half square, this rectangle corresponds. Now to its children, there are two children, there will be these guys corresponding. And what we do, we take, let's call it top I. So if it's I, so if this is I, we draw a square, take the top half and call it top I. So take F and consider the following very simple linear operator, characteristic function of top I. And in any this top I, you put a weight, Wi. So you can think that it's like a piecewise positive weight in the upper half plane. And so the question is, when this operator, so it's embedding, when EF integral in this D w dx dy is less or equal than constant integral f squared dx. So this is why it's called embedding, because this inequality, as you can very easily see, is exactly this inequality. Now, why we embed in such a strange way with this characteristic function top I? In fact, it doesn't matter. You can instead of this discrete dyadic embedding, you can write a certain embedding using Poisson kernel of f or any other reasonable kernel of f. So f is function of one variable, but when you apply convolution kernel like Poisson kernel, you will have two variables because you have like vertical and horizontal variables, and you kind of embed a function on the line to some function which becomes a function on the plane, right? And on the line you have Lebesgue measure. On the plane you have some measure. And you want to know when this operator E acts from L2 with Lebesgue measure to L2 with this other measure. Okay, so you want the condition for this measure W. And Carleson found this condition, and it's an instance of so-called T1 theorem. So let me write this condition. For that, I will erase something. So this embedding turned out to be equivalent to the following. So I'm writing necessary and sufficient conditions. So I'm writing theorem of Carleson. So for every dyadic J, the following should happen. The sum of Wi over I inside J, I again are dyadic, of course, is less than some maybe other constant. And here we just write J. So this is called Carleson packing condition for these numbers. You can, of course, just divide by J. Then it becomes this condition. So that's a Carleson packing condition, and it's necessary and sufficient. And the, of course, if you have constant C, you will have a certain constant C tilde, and the other way around. So this constant can be recomputed one for the other. And to remember this theorem is very easy because it says this inequality, this embedding happens if and only if it happens for characteristic functions f. So this is so-called instance of T1 theorem. To check that a certain operator is bounded, it's sufficient to check its boundedness on very simple functions. It's not even characteristic function of sets, it's characteristic function of intervals. So that would be enough. So this is what Carleson proved. And now, well, let me reformulate it. So for example, suppose I don't want to have the average, but I want to have just integral. Of course, it doesn't matter. Because I can divide and multiply. And the condition for this thing, so this is just the same thing, I just change variable, will be this one. And so I just change variable, right? Again, I just check my inequality on characteristic functions. Nothing else. So, but of course, when I check on characteristic functions, so I will have this I squared coming from here, So that's no problem to see what happens. Okay, so this Carleson embedding theorem was used in many places, in corona theorem, it's actually the same as saying when that paraproduct operator is bounded if its symbol is in BMO. It's exactly the same claim. I don't want to translate one to another. It's sort of triviality. But then people were asking the following very similar question. So suppose now you are doing the same thing, but not with dyadic intervals and not with dyadic squares. By the way, this theorem has nothing to do with dimension 1. If you are in dimension 2 or 3, instead of dyadic intervals, you consider dyadic cubes, and exactly the same claim happens, and exactly it's very easy to remember. You write embedding, and it's true if and only if you check it on characteristic function of, say, cubes, dyadic cubes. So it's always like that. So dimension has nothing to do with this problem. However, let us now consider not dyadic squares or cubes, but dyadic rectangles. So we are now in, say, in dimension 2. We have a function on the unit square. So unit square is our root. And then we have many dyadic rectangles. So these two guys are children of dyadic square, but those two guys are also children, so up and down. So now you have 4 children, right? So if you try to draw the graph, so this is the root unit square, then there are like vertical children, they're like horizontal children, right? And now you need to continue, but then you see the graph suddenly becomes to have cycles, because this guy has this child, but this guy also has the same child. Okay, so these two things who are children of the root have the common child. So one node in this graph will have 2 predecessors. If we would do it for the one-dimensional case, or even for multi-dimensional case, but not for dyadic rectangles, but for dyadic cubes, this would never happen. That would be a tree. There would be no cycles. But here, when we deal with rectangles, there are cycles in this graph. But graph will appear a little bit later. Now just consider the same problem. So the sum over dyadic rectangles. So integral f d mu dx dy dm2 squared. Then you have some positive coefficients. You can think that these guys are attached to each node, because each node is the same as the dyadic rectangle. And you ask the question again, so integration over the square, f square dm2. And so same question. And that would correspond to B-parameter paraproducts, which I don't want to introduce this new notion or whatever, but these B-parameter paraproducts are important features in PDE. And so here is the question. So when it's true, so can we repeat the Carleson answer? So meaning, is it true that let's write the hypothetical necessary and sufficient condition, that for every dyadic rectangle R tilde, the sum, so we just put here the characteristic function of R tilde. So it will be measure squared, WR, summation will be only over guys inside, and this may be some other constant, and here it will be R tilde. So we have this condition embedding 1, and we ask whether 2 is equivalent. Of course, in this direction, it's obvious, because we just took a special f, which was characteristic function of R tilde. And this is just by choosing f, characteristic function of R tilde. And in d-adic cube case, the opposite was true. Is it true now? It turns out that it's not. So the counterexample was constructed by Carleson. It will be, we will see a little bit about that later today. So this condition 2, which we will call box condition, turns out not to be correct. There is a paper of Terry Tao where he explains the example of Carleson. It's much easier to find than Carleson's initial paper, because Carleson actually never published it. It's 1974. Okay, and then Alice Chang found the necessary insufficient condition. So let me try to write down condition of found by Alice Chang. And this condition found by Alice Chang served as a base of a whole theory of Robert Pfefferman and Alice Chang about so-called product BMO or B-parameter BMO. It's a very interesting subject, but we will not touch it. Instead of, we will just write what Alice Chang invented. So invented condition number 3. It's very natural, but funny. So big C, 2 tildes. So instead of checking condition number 1 on characteristic functions of rectangles, now you should check condition number 1 on characteristic function of, say, finite union of rectangles. So again, there is nothing here. This direction is trivial. One second. Okay, so in this direction, it's again trivial. It's highly non-trivial in this direction. And again, so now picture becomes clear. Box condition doesn't work. Carleson-Chang condition, let's call this Carleson-Chang condition, now works. So that's the answer. Okay, now it was very natural to ask why we start with Lebesgue measure. Why on these 2 slides measure is Lebesgue measure. There's nothing very special in Lebesgue measure. So suppose we start to integrate with mu. Not with Lebesgue measure, but with some measure mu. And of course, here it should be also mu. And then it turns out that the answer is exactly as before. You just check on characteristic function of intervals. Instead of I squared, you will have mu I squared, because now you will have mu inside, mu I squared. And on the right-hand side, instead of length of j, let's forget about this thing. Instead of length of j, you will have mu of j. So again, you check on characteristic function of intervals, and it turns out to be necessary and sufficient for this result. So what about Carleson chunk in this case? So let's write down. By the way, what I just said, that you can replace Lebesgue measure by any other measure, and the answer will be exactly the same. It's was done by Eric Sawyer. And again, it doesn't matter in which dimension. What matters is that this should be dyadic lattice. It should be cubes, dyadic cubes, not dyadic rectangles. So if we replace Lebesgue measure by some other measure, we will have this will be embedding, which we like to have, for which we would like to have the, suppose it's again square, dimension 2. So this is what we want to have. And we ask now, well, box condition obviously shouldn't work, right? Because it's already didn't work for Lebesgue measure, but we ask whether this condition will work. And omega is the finite union of dyadic guys. How many doesn't matter, it should be any number. So let's, by the way, for the future purposes, maybe call finite union of dyadic rectangles dyadic or open set, even though it's not open, but let's call it dyadic open set. So this is the condition, say, again, we can call it Carleson-Chang condition, and you're just checking the condition on dyadic open sets, and you want to know whether it's necessary and sufficient in this direction, of course, trivially yes. And the opposite direction, in the opposite direction, nobody knows. So it's well, what does mean nobody? Nobody knows. So Carleson counterexample shows that it's not true. No, Carleson doesn't show that. So nobody knows. Not only nobody knows this, but nobody knows what is the real answer. So it's open.
So, Sasha, may I ask you something? Not even if the measure is, you know, omega dx for omega, some kind of weight or something, nothing is known?
Well, my talk is exactly that for some, these guys, it's not.
Okay.
So.
Oh, no, I'm thinking the mu.
For mu, for very simple mu, it's trivially true. So if mu is a tensor product of two measures, one in one variable and another in another variable, that's the right answer. But for real measure, which is not the tensor product of things, it's not known. Okay, so let me maybe erase this, at least partially. And now let's work on graphs. Because you probably noticed that dyadic intervals is just a dyadic tree, dyadic cubes is some other tree, and dyadic rectangles is not a tree. Dyadic rectangles give you a certain graph, which we will call T2, and it's actually direct product of two trees. And the same will be with Tn. And so we will be working on these graphs. And so now I will a little bit generalize what we are doing. And so on this graph, and we always, for simplicity, think that all these T's are finite. They're huge, no bound of how big they are, and no estimate should depend on how big they are, but just to understand, to have a picture in front of you, let's think that they're finite. And on these trees, and by the way, also on just the usual tree, simple tree, you have an operator. So operator, so if you have a function f, say on 3 to positive numbers, you have very simple operator, I f of alpha. Alpha is a node, it's a vertex, and you just sum f of gamma, gamma bigger than alpha. If you think about intervals, because it's dyadic intervals after all, nodes is dyadic intervals, bigger means that this dyadic interval contains this dyadic interval. So there is a root, which is 0, 1, and so it's all these alphas, gammas, they're like that. Okay, so this is the operator. It has a formula joint. So summing down. So this first one is summing up, second is summing down. And the same happens on any tree or any multi-tree. So instead of, so I would like to distinguish between simple tree and multi-tree. I will write two guys, two lines. But now big O equal has exactly the same meaning, that rectangle contains a rectangle. But now you can understand that one guy can have two fathers, or if we are in higher dimension, can have many fathers. Okay, so this graph, so this big O equal is the order, but it's not a linear order, it's a partial order. Okay. You can also imagine it like that. So gamma or alpha is gamma 1, gamma 2. Alpha is also alpha 1, alpha 2. And big O equal, well, means what it means in this partial order. So that one rectangle is containing another rectangle.
Sasha, before, sorry for interrupting so much, but you will include all parents, right? In the sum.
Yeah, all. If we
Okay.
sum up, we sum up over all guys
of them.
which contain alpha, right? If we sum down, we sum over all rectangles which are contained in beta. Okay. Okay, so what I what will be our question? So our question will have two ways to formulate. So one, we're interested in the following. We're interested in this. And the dual formulation. Now, by the way, what is integral over Tn f squared? It means that I have no measure here. It means that the measure is it's a counting measure. So I just sum squares over all vertices of the graph Tn. So if you like to have a second measure, because before we had two measures, right? Mu and W, you can always write this W here. Okay, but my main thing will be about very special W. W equal identically 1. Okay, so in particular, I'm interested in this question. So to give necessary and sufficient condition for this thing, when there is no W. Well, there is a W, just 1, 1, 1, 1, 1, 1, 1. Okay. The dual formulation of the same question is the following. So we have a dual operator. And again, this is Tn. This is Tn. Now we can ask, how about n equals 1? For n equals 1, it's the same as Carleson and Sawyer. It's answered, Irina and I. It's a small generalization when you, when you have.
We lost the iPad.
I also
Okay.
lost 1 second. So it's a small generalization of Carleson and Sawyer theorem, and so we did it with Irina, and it's exactly the same answer. So you just check it on simple test functions, and the answer is the same. Okay. Before going to n equals 2, which will be main subject, well, maybe also n equals 3, we'll see. Let me tell you that our condition, this embedding, this is what we're interested in, to give necessary and sufficient condition for measure mu for this to happen, is exactly equivalent to this inequality. And this inequality, as you can see, this angular brackets is the average over the whole graph with respect to measure mu. So you integrate with mu and divide by mass of mu. So it's a Poincaré inequality. So we are given necessary and sufficient condition for weighted Poincaré inequality. So here is our some arbitrary weight on the graph. And so we want to give necessary and sufficient condition for this pretty classical Poincaré inequality to happen. It turns out that these two things are equivalent. It's not very difficult to prove. I don't have time to do that. And of course, this direction is obvious, and this direction is not so obvious, but not very difficult. Okay. Now, why it's Poincaré inequality? Poincaré inequality should have derivative on the right, should have gradient, right? And here we actually do this, because if we change the variable, so that's a new function, then of course here there will be this capital F, here there will be capital F, here capital F, and you should think about this summation up as the integral. And then small f is sort of a gradient of capital F. And in fact, of course, we can write it in this form. We can change the variable. We can write here capital F, and here we can write the gradient in the right sense. It will be some discrete sum over certain neighbors squared, and this will be exactly Poincaré inequality in the normal sense. Okay. So, all right. So let me. So here, yes?
Well, if n equals 1, what is this gradient?
If f equals
n equals 1 in diagonal 3 case.
3 case, n equals 1. So what is what?
What is this gradient of
gradient are very simple. It's just if you have a node and a son, the gradient at the son is just the difference between father and son.
So gradient is a function, so scalar values, right?
Yeah. Gradient will be in this case just a function, right? Okay, so let me explain. This is what we're trying to do. So I don't know why it's call it alpha. It should be called W. So again, I already told you that if we have this general embedding with two weights, to ask whether this is necessary and sufficient is senseless, because even for Lebesgue measure mu, Carleson showed that it's not sufficient. If omega is just one, if omega is a box. And Chang, for this special case, showed that if omega is not a box, but the union of boxes, then it's necessary and sufficient. So we again can ask whether for the general mu and w, this is a necessary and sufficient condition. And the answer is no. And again, I repeat, nobody knows the real necessary and sufficient condition. And what we will be doing now is that for n equals 2 and n equals 3, and w, which is identically 1, but mu arbitrary, will give necessary and sufficient condition. So this, first of all, this necessary sufficient condition will be this one. Again, Chang, Carleson, as a sort of one would like to expect. But the most amazing thing that even box condition is necessary and sufficient, which seems to be contradicting to Carleson counterexample, but it doesn't. Because in Carleson counterexample, W are quite complicated. Okay, so my main goal now will be explain why box condition is sufficient for the embedding for this particular dimensions, what is the difficulty we have to put it to other dimensions, and why W equals 1 is an important question. So why W equals 1 is an important question is easy to explain. There is a whole theory of embedding of holomorphic functions on polydisk. So you have a certain class of Hilbert space of holomorphic function on the polydisk, and they have norm. For example, this Dirichlet norm, you take derivative, take square, integrate over the polydisk, you get the norm, Dirichlet norm. And now you're interested in measures such that if you integrate f squared with respect to this measure, and measure is inside the polydisk, you will have a bounded embedding with respect to this norm. It's story, it has long history, this kind of question from Corona theorem, and it's many interesting things about such embeddings. And it's about holomorphic functions, say of Dirichlet class. By the way, there is a whole scale, like there is functions of Dirichlet class, then there is a function of Hardy class, and in between there is a whole scale of spaces of holomorphic function, Hilbert space of holomorphic function. And for every one of them, it's interesting to understand what are the measures where you can embed this thing. Mostly it's not known. And the second thing is that it cannot be about positive functions. These functions are holomorphic. And amazing thing, it's soft analysis. It's not hard analysis, but it's very beautiful that for certain scales like Dirichlet spaces, you can, without loss of any information, translate the question from holomorphic functions to my question on graph, on T2 or T3. T2 if it's two disk, if it's disk cross disk, and T3 if it's disk cross disk cross disk. And again, Tn if it's d to the power n. So there is a certain certain trick, certain mechanism, which one-to-one correspond one problem to another problem without loss of any information. So if you answer one question, you answer the other, which is sort of very amazing, but it's true. And for that, you need W equals 1. If you speak about Dirichlet, it's exactly W equal 1. If you speak about something, it's a whole scale of spaces, not only Dirichlet, then this W should be a little bit more general than 1, and we also can do that. Okay? But W equals 1 is leading particular case. It's as difficult as all other cases we can treat. And all these other cases give the result for embedding of holomorphic functions. Okay, so now our W will be 1 for simplicity, and also because it's very important particular case. And here is, I again repeat Carleson counterexample that there exists a certain collection of W's on double tree. And moreover, you can take here just Lebesgue measure such that this condition is satisfied, but there is no embedding. But as I already said, we will be considering this special case, and this is absolutely not what Carleson did. It's very far from that.
One question.
Mm-hmm.
So you are saying that there is a question on the polydisk,
Mm-hmm.
and what you are doing on the graph, you are solving that question. Am I right?
Yes. So there is a certain dictionary which translates the question on the polydisk to the question on T2 or T3 or Tn, and you don't lose any information.
Okay, now you solve the question on the graph when n equals 2 and n equals 3. So did you get a new result on polydisk, or you already knew the answer on polydisk? Or
no, nobody knew the answer on the polydisk. So it's a new result.
No problem on the polydisk, am I right?
Only on B disk or 3 disk. For 4 disk, we don't know.
No, can you write down what is this problem on the B disk?
On B disk, yes, I can. So we're on B disk. So we write integral d2 f squared d mu. Mu is the measure inside the disk. You can write it in form of Poincaré, or you can write it like that. And then you want a constant, which would work for every f. And on the right, you should write Dirichlet norm of this thing. So Dirichlet norm can be written in several ways. For example, one is, dz1, dz2, f squared, and it's also B disk, and here is the volume on the B disk. Okay.
Okay.
It should be 2 derivatives. So Dirichlet on B disk will have 2 derivatives. It's the correct thing. Okay, so here is the theorem, which I should write here, actually n, but n is 2 or 3, or 1, but 1 is a trivial case. And this in means summation up on Tn. So it says, well, you see, we take W equals 1 here, so you can forget about W in here, but I would like to say a word what kind of other W's will work. So you sum up this thing, sort of integrate up, square d mu, it should be less than f squared dw. It's embedding. it's the same as the dual embedding. So this is the dual embedding. You see the role of mu and w change, and summation up becomes summation down. And it turns out that it's equivalent to Carleson-Chang condition. So you take any finite union of rectangles, or in this case, you can think about finite union, any finite union of nodes on this complicated graph, and you are summing up over everything which lies down any of them. Okay, and there is no f anymore, it's just mu and w, and this is Carleson-Chang condition. And this sufficiency is difficult. But what is most amazing is that you don't need to take union of Carleson boxes. You don't need here the omega. You can have just one vertex. So you can have box condition. So this last 4 to 3 is the most difficult claim. And it's absolutely amazing. Let me explain why it's amazing. Maybe I should amaze you. So it's a combinatorial property of all measures on the unit square. So all positive measures on the unit square has the following amazing property. You see, I spoke with some people in geometric combinatorics, very good people. And for like a couple of months, they were trying to construct the counterexample to this claim, because the claim should be wrong. So here is the claim, which is true. So if measure has the following property, for any dyadic rectangle, the sum of mu r squared is less or equal that mu r tilde. And your summation is over all dyadic rectangles inside r tilde. So suppose we have this property. So then measure will have the following property. The sum of mu r squared less or equal to some absolute constant, mu of the union rk, any union, and here you should sum up over all guys inside the union. You see, if they were disjoint, that's triviality. Of course, from here we go to here by just summing over disjoint things. But dyadic rectangles, they intersect like crazy. So the overlap can be absolutely impossible to take care of. And however, that's true. That's always true for any positive measure in 2 dimensions. And it's also true for any positive measure in 3 dimensions. And we have no idea whether it's true for any positive measure in 4 dimensions. Okay, so let me erase this stuff. So Fedor Petrov was trying to build a counterexample for quite a while. And then it turns out that counterexample may exist. Well, here I tried to explain the Carleson counterexample, but maybe I don't have really much time to do that, so I will skip it. And again, I come back to this question which we consider. So I integration up would like to be bounded in L2 mu. So we would like this estimate on B3.
But Sasha, you have boundary of t square under the integral. You are summing up over the vertices, or
again? If what?
You have integral of the boundary of t square on the slides.
1 second, something happened. What should I do with this? Okay. All right. So again, Pata, what is the question?
My question is about the notation. So you have integral over the boundary of t square on the.
Oh, here. It's actually a little bit. I mean, you can forget about this.
So it's a usual sum of the vertices of the. Okay.
Yeah. So it's just particular case when it's boundary. It doesn't matter. So here is maybe you would like to write it down and try your skills. So it's actually one-dimensional case. It's not two parameter. It's one parameter. It's one parameter Olympiad problem. Okay. Well, it's not. I think it's not so difficult as to deserve the name Olympiad problem, but it's not so easy not to deserve it. So you have dyadic tree. And at each node, you have a positive number, which is the sum of two positive numbers at suns. Okay. You also have another property that is written here. So if you fix a node, this will be J, and then consider all guys which are below. This will be all i's, many i's. And you have this property. So two properties. So the guy at father is equal to the guy to sons. And also we have this second property.
Muse J square. I guess square is missing, right?
No.
When I equals J, you get on the left-hand side.
Well, you just get that they're all less than one. That's true. They're all less than one. But what I want you to prove that not that less than one, but they have this property. So the length of I is basically 2 to the minus n. So if you go n steps down, you should get the estimate that on the nth step down, this measure is less than constant divided by n. That it decreases at least linearly in the reciprocal sense. C divided by n. So it's sort of Olympiad problem. So it follows from what we did.
Is it a regular dyadic tree or no? This could be the
That's absolutely regular dyadic.
Okay.
It's even not.
I mean, that's for the
double
picture.
tree. No, not even double tree. So on the double tree, you have a more complicated inequality. So if P is a rectangle, then you will have this inequality. Okay. If it's a rectangle I cross J. But even for dyadic tree, it takes some thinking to prove that. Okay, so now I would like to explain the essence, why it's difficult and what we did. And even I would like to prove, but I don't have time. I really want to prove the main result. I would like to give the wrong proof. Because the right proof is not, well, it's very good proof, but the wrong proof is much more instructive. So, but first I would like to explain the difficulty. The difficulty is that on the double tree or triple tree, we don't have maximum principle. So let's introduce the potential first on just usual tree. So we have usual tree. And we have a measure. At each node, we have some non-negative number. And you do the following thing. You first sum them down from any alpha, and then you sum that up. Okay, you first generate one thing, summing down, then this is called potential. Now, this potential has the following property. So let us introduce the following thing, V mu delta. So here on the simple tree, let me write one stick, not two sticks. So on the simple tree, what the definition of V mu delta, it's the same thing, but you are summing only over the places where this is less than delta. So what does it mean? So you, you have a certain positive function, and you look at the places where this summation is less than delta. And then you should notice that this is this thing is less than delta everywhere. So suppose at this node, your V mu is less than delta. Then of course this thing is less than delta, obviously. But suppose it's not. So here is any so here is any node, and you are summing up. So somewhere here you will meet a place where V mu is less than delta, and you're summing up like that. And so and before that it's not less than delta, so you are not summing at all because you cut like this. And so V mu delta obviously uniformly is less than delta. Now what happened on the B tree? On B tree, nothing like that will happen, because if you are on the B tree and at this node your summation is not less than delta, this thing is not less than delta, you can reach many predecessors where it will be less than delta, and sum over all of them, each of them will be less than delta, but together they will be not less than delta. So let me formulate it in a different way. So suppose the potential V mu is less or equal than 1 on support of mu. So if it would be on the usual tree, it would mean that uniformly V mu is less or equal than 1 everywhere. On the B tree, that's not true. So V mu can be less or equal than 1 on support, but the potential can be as large as you want somewhere. And one of the main difficulty is to understand how big is this set. So there is no maximal principle on multi-tree, and so we need to replace maximum principle by something else. So for that, let's introduce energy. It's energy. And let's introduce kind of cutoff energy. So by the fact that on the usual tree, V mu delta is uniformly less than delta, because if you go up, you meet only one guy, it follows that E delta mu, well, it's uniformly less than delta, is less than delta times mass of mu. So we can think about this inequality as sort of maximum principle. And that the fact that delta is to the power 1 kind of tells us that it's a maximal principle, because it just follows from this trivial inequality. Now, as I said, you cannot do this with this guy, because V mu delta can be much, much bigger than delta somewhere. But it turns out that if you integrate in average, you will get something better. So let me formulate what we get. For that, I will erase something. So it turns out that this cutoff energy is less than some universal constant delta 2/3 on B3. Actually, on B3, there is an even better result. Maybe I will tell it. And on 3-tree, we have another estimate, which is, as you can expect, is worse. On 3-tree, we have something like that. It's on 3-tree. So well, let me just, so this is we call surrogate maximal principle. And the surrogate maximal principle is the main tool to prove all our things, that Carleson chunk is enough to have embedding, or if we have just box condition, it's also enough to have embedding. And again, this is like one of the main block, and the main block to prove this main block is the following result. And this result I want to spend maybe 1 or 2 minutes to give a wrong proof. And when I will give the wrong proof, you will get the idea how interesting and tough is the right proof. So here is the certain optimization principle. So suppose we have a function on, well, our function is non-negative on double tree, and it has the following properties. It's super additive. It's like before in this example. So measure at father, now not equal, at big or equal, then not measure. Function at father is big or equal than the function in 2 vertical guys, or the same with the 2 horizontal guys, because we now have 4 sums. Okay, so we have super additive function, and here is the property that its support lies where integration is less than delta. The support of this function lies where the integral of this function is less than delta. Take a large lambda, and then there exists some other non-negative function such that it integral majorizes integral of f on a certain set, but its energy is much smaller than energy of f. So this is the main result. So this result gives this surrogate maximal principle. The surrogate maximal principles give us embedding, etc., etc. So I would like to show a little bit how to prove this theorem, but I will intentionally give the wrong proof. So there are several other such majorization principles here, but let's try this. So let's draw the picture. So the proof will be by picture. So we have a positive function, and we have 2 numbers, delta and lambda. Now, we should somehow incorporate into this picture that support of f lies where if is less than delta. Suppose this is some node of our tree, and this is the root. So this is the unit square. It's of course higher than our node. So this is some rectangle. It's some dyadic rectangle, and there are 2 dyadic rectangles which can say that this guy is their father. So I will draw them here and here. Now I will start to fill up this table of dots. So here I will write the value of f. Here I will write the value of f on this one of these fathers. Here I will write the value of f on another father. And here is the rectangle which fathers this both fathers. And here I will write the value of f on this one. And I will continue doing that. So I will have the whole, right, table of numbers. And here is, I will have f at the top. Now, what does it mean? What is this set if less than delta? So if it would be on the usual tree, our picture will be like that. So here, this the root, this is my interval, and these are all intervals which lies between them. And this is a linear thing. And somewhere integration up will give me less than delta. And it's exactly this thing, right? So how it looks on this picture? Well, on this picture, it looks more complicated. So here is the figure where integration up is less or equal than delta. So for example, they have such corners. So here it's less or equal than delta if we sum up like that. Because IF is summation over guys which are over this guy. And over this guy is this rectangle. So for example, this is also less or equal than delta if I sum up over this rectangle, all these numbers. But it doesn't mean that if I sum up over all these guys, it will be also less than delta. Here it is. If I sum up all of them, it will be less than delta because this is only what I'm summing, and this is less than delta. Well, here it's not. We're summing up many, many rectangles. So how big is that? We don't know. So it's another instance to explain that we don't have maximal principle. But, so what we want phi such that, so there was a condition that at this place, our IF, summation over all square, over all table, is much bigger than delta. So this is where summation over each rectangle is less or equal than delta, but here it's much bigger than delta. It's between lambda and 2 lambda. Okay, and so and now we want phi. We want to redistribute the values of f in the following way: that at this point, the summation over the same table for phi will be bigger than the summation over the same table for f. So there should be majorization. So I phi at this, let's call it omega, should be bigger than IF of omega. But the energy should be much smaller. The integral f squared, phi squared, should be much, much smaller. And I think it's even squared here. So here is the proof, a very simple proof. So here our value, by the way, this table has a very simple property. If you go right or you go up, the values of this table go up. Because of property of f that it's super additive. So by super additivity, this table grows in this direction. It goes to the right, it goes to the up. Okay, so and here between lambda and the sum of all guys is between lambda and 2 lambda. All right, so let's find the place where if we sum up not the whole table, but only below this red line, it's approximately 3 lambda over 2. Okay, now notice, so this is 3 lambda over 2 if we sum up all these guys up. And if we sum up only those guys, it's only delta. But the guys here, because the table grows, they're all sort of bigger than those which are to the left. So if we sum up like this, all these vertical things, it is bigger than, I mean, each of them is bigger than the guy here, than any guy here. But they sum up only to delta. And those guys basically sum up to the whole lambda, which is much, much, much bigger. So what does it mean geometrically? It means that if we're summing up bigger guys and get much smaller than if we sum smaller guys, it means that the number of summation is much smaller. So it means that these points, the number of points here, the number of vertical lines, is much smaller than the whole number of vertical lines. And how much smaller immediately we can see, it's the proportion should be delta over lambda. Now it's a very simple calculation. So if sum of bigger guys is smaller than the sum of smaller guys, and actually this much smaller, it means that just summation is very, very short. Right? So the positions here, much smaller position than positions here. But our F was concentrated only here. Support of F lies inside this strange figure. So let me, but nobody asked us the same about support of phi. Phi can have any support it wants. So let me take these numbers, these values of F, and equidistribute the sum of them over all points. So I have now a long drawer where to put my numbers. So I take the sum of F and I distribute them equally here. So if you just, sum will be the same because we just distribute them equally, but sum of squares will be much, much smaller. Right? If you distribute 1 as 1 over 10 plus 1 over 10 plus 1 over 10 plus 1 over 10, the sum of squares will be very small, not 1. And so we are done because we distribute the sum. So I phi will be the same as IF. We do it in every line. And sum of squares dropped, obviously, by delta over lambda squared. So we're done. Our optimization, our majorization with dropping of energy is already proved. The only problem, there are 2 mistakes. Anybody see one mistake or 2? It's a very, very good proof in the sense that it's very instructive. It shows what kind of combinatorial morass you should deal with. So there are 2 mistakes. So one is not very serious. Maybe it can be dealt with, but another is very serious. So one is that on this red line where we divide it approximately in 2, everything is okay. And below it will be also okay. Because below the number inside our figure becomes even smaller. Figure is always like a stairway like that. So it becomes even better. And we again can distribute and it looks like it's fine. But there is a small problem if we go up. So now it's not constant times lambda, it can be much smaller. So the number of places becomes much smaller. So there is something wrong with this fraction. Well, this problem can be taken care of. But there is another problem, which is very serious and which actually shows that this majorization theorem is a very serious theorem. The problem is that if you do it for this omega, you have some redistribution. But then you should repeat it for every picture. There is not one omega. There are millions of such pictures. But so these pictures will be different because omegas will be different, but they will be glued together somewhere inside. So if you distribute, so your redistribution should be done in a way which remembers what it has already done. So it should reconcile many inequalities. So it's a certain convex optimization problem which cannot be solved like that. Because if you do it for one omega, then when you do it for another omega, your guy here can be completely different value. So you should do redistribution thinking about all omegas at the same time. And this is very difficult to do. Let me, sorry, let me finish by just some, some claims. So we said that if if a potential is less than 1 on the support, it can be very large somewhere. So how large and where, on which kind of set? It turns out that where it's bigger than lambda, where lambda is a very large number, can have a certain estimate. So on B3, the capacity of such sets decrease like the 4th power of lambda. Capacity is a very natural notion for this stuff. We just consider all positive function such that summation up is bigger or equal than 1 on the set, and take the infimum of energy of such functions. So infimum of L2 norm. So that's capacity of the set. So this is the result which follows from this principle of homogenization on T2. On T3, we have a little bit worse. We have absolutely no idea how sharp is that, because the only example we have is that we can have the measure on B3 less than 1 on its support, and such that capacity of the set of large values is exponentially, is order of exponential. It's not lambda to the power. It's not 1 over lambda to the power. It's exponential. And there is a drastic difference between estimates from above and estimates from below. So we don't have neither example which comes closer to that, nor the proof which makes it exponential. So we don't know. Okay, so maybe, yes. Remember this delta to the 2/3, delta to 1/2, and just delta to the power 1 on the simple tree. The simple tree is delta to the power 1. Recently, we improved our 2/3 on double tree to almost delta to the power 1. So here is the estimate. And so it's like delta to the power 1 minus tau for any positive tau. But the proof works only on this guy, but doesn't work on T3. So on T3, we still have square root of delta order, so we don't know. And now just 5 seconds, well, not 5, maybe 1 second or 1 minute to explain how the real proof works. So how this phi is constructed.
Sasha, we are negative 30 minutes.
Just
it's some time for questions.
Okay, it's so beautiful. It's just one slide. So it's this lemma. If you have this lemma, you have phi, and phi is written here. it's just, you see this calculation wise fees is majorization is here, and then energy is another slide. But let's forget about checking that the energy will become small. Let's just look at this lemma. So lemma is algebra. So it says this, and let me just tell you why this lemma is correct. Let's think that we apply to this supposedly correct lemma inverse operator, which doesn't exist, I minus 1. If I is the integration, that I minus 1 is differentiation. So we differentiate the square of the function, but we differentiate it in both derivatives, d1 and d2. So when we differentiate square with respect to d1 and d2, I'm saying absolute stupidity. You cannot do that. It's stupid. It's impossible. But it explains the lemma. So if you differentiate, then you put d1 on one of if, and you put d2 on the other if. So because you apply I minus 1, this disappeared, and you get this term and this term. But then you can put both of them on one term, and then they cancel I. And this is why f appears. But there are two guys, if and another if, and so another if stays. So I explain how this lemma should work. Well, in fact, if it would work like I said, the constant would be just 2. In fact, the constant is some absolute constant, and the checking this lemma is just checking that that's true. Of course, not by differentiation, true by some strange algebra. So, and after this lemma is proved, then you just by some very simple calculation, you can see phi. The one phi which will actually do the job for this majorization. And so majorization is already here, proved here, and energy can be again proved by, it's actually proving the energy estimate is the most difficult part, but I don't have time to explain it. And so here I will stop. Okay, questions?
Okay. Looks like Irina disappeared. Okay, are there any questions?
No, I'm here.
I have a question. In the B-disk inequality that you wrote down, can you scroll it to that slide? I don't understand. If I take f of z equals z1, right-hand side is 0, left-hand side is...
Well, I intentionally wrote it slightly incorrectly, but...
mixed derivatives, right?
So let me write it again. So you need integral f squared. So maybe you should actually eliminate the constant.
Okay, so stop. Ah, okay, you're subtracting 0, not average. No, still, f of z equals z1.
Yeah. So you should actually write a little bit more. Same with z2.